Now, in this competency 4, we are going to analyze CSTRs in series. A first-order reaction with no change in the volumetric flow rate, that means B equal to B0, is to be carried out in two CSTRs placed in series, as the figure indicates. So we have two reactors. In the first reactor, the reactant enters at CaO, the concentration CH0. They leave the first reactor with a concentration CH1, and they leave the second reactor with a concentration CH2. So the effluent concentration of reactant A from the first CSTR can be found using the equation that Ca1 is equal to Ca0 divided by 1 plus tau 1 K1, and with tau 1 equal to the volume 1 divided by the volumetric flow rate at the entrance. From a mole balance on the reactor 2, the volume 2 of the reactor 2 is going to be Fa1 minus Fa2 divided by minus Ra evaluated at 2, which is equal to B0 times Ca1 minus Ca2 divided by K, the rate constant K2, at Ca2. If we solve for Ca2, the concentration exiting the second reactor, we will obtain that Ca2 is equal to Ca1 divided by 1 plus tau 2 K2 is equal to Ca0 divided by 1 plus tau 2 K2 times 1 plus tau 1 K1. If both reactors are the same size, then tau 1 equal to tau 2 equal to tau, and operate at the same temperature, then K1 equal to K2 equal to K, then CH2 will be CH0 divided by 1 plus tau K to the second power. CSTRs in parallel. We now consider the case in which equal-sized reactors are placed in parallel rather than in series, and the feed is distributed equally among each of the reactors. So we will have three reactors in parallel, and we are going to distribute the molar flow rate at the entrance in 3. We are going to give 1/3 of the initial Fa0 to each of the reactors. And so, the balance on any reactor, let's say I, give the individual reaction volume Bi equal Fa0 times Xi divided by minus Rai. Since the reactors are of equal size, operate at the same temperature, and have identical feed rates, the conversion will be the same for each reactor. X1 equal to X2 equal to Xn equal to X, as will be the rate of the reaction in each reactor. Ri1 is equal to minus Ra2 equal to minus Ran equal to minus Ra. So, the volume of each individual reactor, Bi, is related to the total volume of all the reactions by the equation Bi equal B divided by N, where N is the number of reactors. A similar relationship exists for the total molar flow rate, which is equal to divided F0I is equal to Fa0 divided by N. Substituting these values into the mole balance equation yields B divided by N is equal to Fa0 divided by N times Xi divided by minus RAI, and B equal Fa0 times Xi divided by minus RAI is equal to Fa0 times X divided by minus RA, the rate. This result shows that the conversion achieved in any of the reactors in parallel is identical to what would be achieved if the reactants were fed in one stream to one large reactor of volume B, which is the sum of all the individual volumes. A second-order reaction in a CSTR. For a second-order liquid-phase reaction being carried out in a CSTR, the combination of the rate law and the design equation yields the volume equal Fa0 times X divided by minus Ra. This is equal Fa0 times X divided by K Ca squared because it's a second order. Using our stoichiometry table for constant density, where the volumetric flow rate is the volumetric flow rate at the initial, we will have that Ca is going to be Ca0 times 1 minus X, and Fa0 times X is equal to V0 Ca0 times X. Then we will have that the volume B is equal to V0 Ca0 times X divided by K Ca0 squared times 1 minus X, all that square, divided by V0, we will have that tau is equal to X divided by K Ca0 times 1 minus X, all that to the square. We solve the equation for conversion X, and we will have that X is 1 plus 2 tau K Ca0 minus 1 plus 2 tau K Ca0 squared minus 2 tau K Ca0 square, all that to the 0.5, all that divided by 2 tau K Ca0, and we get this by the equation of the quadratic expression. So at the end we will have that X is equal to 1 plus 2 dA minus 1 plus 4 dA elevated to the half, all that divided by 2 dA. And so here we have the conversion in function of the Dunn-Coll number, which is very easy to calculate. And the minus sign must be chosen in the quadratic equation because X cannot be greater than 1. And conversion is plotted again as a function of the Dunn-Coll parameter tau KCA0 in the next figure. Observe from this figure that at high conversion, they say 67%, a tenfold increase in the reactor volume or increasing the specific reaction rate by raising the temperature will be necessary. The conversion only to go to 88%. This observation is a consequence of the fact that the CSTR operates under the condition of the lowest values of the reactant concentration, the exit concentration, and consequently the smallest value of the rate of reactions. So here we see that for a small change in conversion from 0.67 to 0.88, we will have a very big increase in the Dunn-Coll number and as a consequence in the volume of the reactor.